now is not going to be so lengthy as 2.2, going to give us a little bit of a break. Talks now about one-sided limits. Okay. Section 2.4, one-sided limits. Okay, this is not a lengthy section. Yep, I can move that piece of paper down so you can actually see it. That would be nice, wouldn't it? And very briefly, I'm going to start this by reading a couple of, just a short paragraph of information in the textbook, showing it to you and talking about it, getting a little bit of the wording kind of in your head. Okay, and it starts section 2.4 at the bottom of this page after all the lovely homework from 2.3. And it talks right here, it says to have a limit as x approaches a number, a function must be defined on both sides of that x value, and its y value must approach L as x approaches C from either side. Lots of words. Now remember, L is the value of the limit, C is the x value. So as your x value, as you're coming in from both sides of your x value, you want your limit to be L, the height of the function. So it must be approaching from both sides to the x value being approached from both sides to be the same height. Because of this, ordinary limits are called two-sided. So really, when we calculate a limit, we're always calculating as a two-sided limit. However, if f fails to have a two-sided limit, such as right here, limit as x approaches 0 does not exist because the left side is going to -1 and the right side is going to +1. The limit, the two-sided standard limit as x approaches 0 is not defined. So if f fails to have a two-sided limit, it may still have a one-sided limit. That is a limit if the approach is only from one side. If the approach is from the right of this graph, the limit is the right-hand limit. If it's approached from the left, it is the left-hand limit. So the right-hand limit, strictly coming from the right side, the limit would equal 1. The left-hand limit would equal -1. So you can have one-sided limits and even then have the two-sided limit be undefined or not exist. So let's take a look at this. We've kind of already talked a little bit briefly, run into these examples. Suppose we have this limit. I guess I should write this. I don't even know where this is in the book. But if the limit of f of x as x approaches a equals L, then two things must be true. They are that the limit as x approaches a from the right must equal L, and the limit as x approaches a from the left must equal L. Now here's the notation. If you have a little plus sign, this means approaching from the right side, the right one-sided limit, the right-sided limit. Is that how they say that? The right-hand limit. That little plus sign right there is referring to the right-hand one-sided limit, meaning approaching it strictly from the right side. The little minus sign is the left-hand limit, meaning you're approaching it from the left side. So these little symbols to the right and above your x value are telling you which side you're coming in from to come up with the one-sided limit. So here's an example. And here's just a simple graph, okay, with a hole in it. So if they asked me with this example, what is the limit of this function? We don't know what the algebraic representation of this function is, so we'll just call it f of x. If the limit of what is the limit of f of x as x is approaching to from the left side? That's what the question is saying. What is the limit of this function as x is approaching to from the left? Well, if you're coming from the left, how high is the graph as we get close to 2? It's 1. Okay. the limit of this function as x is approaching 2 from the right side. If we're coming in and looking for the height of the graph from the right, we're coming in. What is the height of the function coming in from the right? It is 1. If these two guys are in agreement with each other, then we can say that the limit of f of x as x approaches 2, this is the two-sided standard limit, okay, when it's not limited to one side or the other. These two must be in agreement for this limit to exist. The left side and the right side must agree for the limit at that point to exist. Okay, so let's do like the one in the book. This will be an example very similar to the one in the book where there's going to be a split or a break in the graph. Oh, and that needs to be an open circle, and I mean I filled it in with that pen. This needs to be an open circle. I guess one could be filled. Yeah, we can fill that one. Let this one be unfilled. Okay, and I don't know, call this function g of x or whatever. And let this be a height of 2 and a height of negative 2. Okay, so the limit of g of x, let's come in from the left, as x is approaching 0 from the left. As x is approaching 0 from the left, what is the limit of that function as x is approaching 0 from the left? Negative 2. The limit as x is approaching 0 from the right is positive 2. So the one-sided limits exist. They have definite values. But I can conclude from this one more thing, and that is the two-sided limit of this function is what? Does not exist. Because if those two are not in agreement, the two-sided limit does not exist. So the one-sided can exist, but the two-sided limit's not happening. Let's take a look at a semicircle. Oh, I didn't do that arch so good. Okay, so let this function, this is a semicircle, this is going to be the square root of 4 minus x squared with a radius of 2. And it's defined on the interval from an x value of negative 2 to a positive 2. Now, let's take a look. This is a 2 and this is a 2. Let's take a look at some one-sided limits on this. What is the limit of f of x as x is approaching negative 2 from the right? How's that for some symbolism? X is approaching negative 2 from the right side. What does it equal? 0. What is the limit as x is approaching negative 2 from the left? It doesn't exist. We didn't even have a graph on this side. Okay? There was no graph to the left of negative 2. So we can't approach it from the left because the graph is not even approaching a negative 2 from the left. Okay? So then we would say that, you could even say now, that the limit of f of x as x approaches negative 2 is what? Does not exist. It doesn't even exist on the left side. So I don't have a left side value. Okay, so when you have endpoints like that, you can get a one-sided limit, but you can't get the two-sided limit. So you have to be really careful with those. Really careful. Now I'm going to go in pretty good depth on this one. And this is a graph. I'm going to pull it straight from the book. This is example 2 on page 68. That's an 8. And take a good look at this one. This will really land it for you. This will clarify everything. Okay. There it is. Here's your graph. Crazy, crazy graph, okay? Really weird looking graph. Oh well, whatever. It's going to tell us a lot. Good stuff. Okay, let's see what this question has to say. The limit as x approaches 0 from the right. Here's 0. As x is approaching 0 from the right, do we agree the limit is 1? Yeah, okay. The limit as x approaches 0 from the left does not exist. Now, they put two things in here, okay? They really could have just said this much. That does not exist. And because the left-hand limit and the right-hand limit are not the same, then the two-sided limit will not exist also. Okay, so they really put two questions in one when they made this conclusion. Okay, at x equaling 1 right here. The limit as x approaches 1 from the left, as x is approaching 1 from the left, the height is 0. Who cares if there's a hole in the graph? Limit doesn't mind. Okay, oh, God. Even though f of 1 is 1. Well, I'm not going to go to that. Okay. So the limit as x approaches 1 from the right is 1, right? Equals 1. So the limit as x approaches 1 does not exist because the left and right hand limits do not agree. Now, this is interesting information, but it has nothing to do with the limit. Okay? This is just, oh yeah, that's some cool information, but we really don't need it at all to find the limit. Okay, those are function values. This is not limit stuff. Okay. As x approaches 2, the limit as x is approaching 2 from the left is a height of 1. We got that. The limit as x is approaching 2 from the right is a height of 1. Wasn't that nice? So now the limit as x is approaching 2, two-sided limit, is 1. We're all in agreement. Now this is unnecessary information, but it's extra information. Don't let it confuse you. It just said, well, isn't that interesting that the limit equals 1, but the true function value is a height of 2, because that's where the filled circle is. Okay, that's what they're saying. This has nothing to do with the value of the limit. It's just extra kind of neat information. Okay, the limit as x is approaching 3. From the left is a height of 2. The limit as x is approaching 3 from the right is a height of 2. So its limit equals 2, which, hey, that's kind of cool. It's also the true function value because that's where the filled-in circle is. So are y'all feeling more confident about this? You feel pretty good? This is not difficult. Okay, then you are good to go. Not good to leave for the day, but you're good on that point. That's not the right verbiage. Shouldn't have said that. It's not time to go yet. Now, there's another thing that's kind of interesting, and I think y'all will like this. It's a little more challenging finally. This was part A. Now we're going to take a look at part B, and it's not very lengthy, so be patient. Okay, so there's all your one-sided limits, and you can see that it's not difficult. Now, this is an interesting situation. Limits involving sine of theta over theta. Now, when we get into calculus and we're talking about the limits, they can put theta there or they can put x there. It doesn't matter. In fact, normally we put x there, but they can put theta there. So don't let the notation throw you off in any way. Now, the truth is, the limit as theta is approaching 0 of this function is 1. The way the graph looks something like this. It's symmetrical, okay? Okay. It looks something like that, where the height of the function is 1 as theta approaches 0. Now, we also could write this as x, it doesn't matter, as x approaches 0 of sine of x over x equals 1. And this is something you do want to know because they use this limit a lot. And they need you to be certain you understand that that's what the limit value is at 0. So then they get pretty interesting in the way they ask some questions about this, and it requires some algebraic methods to be able to answer it. Here's an example of the kind of stuff you're going to run into. Suppose they ask the limit as x approaches 0 of sine of 5x over 5x. Now remember, this theta and this theta must be the same. It must be sine theta over theta. So the argument of the function must be same as the denominator. So long as the argument of the trig function and the denominator are the same, this will equal 1. So long as the argument or the angle value that the sine function is working on is the same in the denominator, by that definition, it's going to equal 1. Okay? So what if it says something about the limit as t approaches 0 of sine of k times t over t? Well, by the limit laws, well, do I want to do that? No, I don't think I want to do that here. Okay, so what we can do is we can algebraically manipulate this because we need the bottom to also say kt, right? It must be kt over kt to use that lovely little identity. So what I'm going to do is multiply the top times k and the bottom times k. Well, when you do that, you get the limit as t approaches 0 of k sine kt over kt. So therefore, this equals 1, and the limit of a constant is the constant. By those rules. Are we okay so far? Okay. All right, now it gets a little more difficult. Suppose it asks the limit as x is approaching 0 of sine of 2x over 5x. Now this really doesn't fit the pattern. I want a sine of 2x over 2x. I want a sine of 2x over 2x. I want the denominator to say 2x. So I've got to figure out how to make the denominator say 2x. So to get the denominator to say 2x, there's more than one way of doing this. But I guess if I multiplied it times 2 on the top and the bottom, what would that make happen? Let's see. This would be the limit as x is approaching 0 of 2 sine 2x. And the bottom is 10x, but 10x is 5 times 2x, right? over the cosine 2x, and we still have a cosine x down there. This is going to become 1, and times 1 over cosine of 2 times 0 times 1 over cosine of 0. No longer a limit because I'm actually going to times 1 over cosine of 0 times 1 over cosine of 0. Well, cosine of 0 is just 1. So this is 1/3 times 1 times 1, which is 1/3. So they get a little hairy at times. I'm going to play with it. This is 2 times 0. Here. Reordered the denominator. And guess what? This is the end of the whole section. Okay? So all that was in this section, that goes for a little relief. On the one-side limits was all the graphing of the one-side limits, and then this sine x over x thing. Okay, that's all you have in this section. So that's a relief after the last section being so very long. You guys enjoy your break, and I will see you on Wednesday.